6.5, vectors in r squared and r cubed. So we must be able to consider vectors in both coordinate form and algebraic form. Okay, so this is what we're going to be focusing on. In this section, we will extend our previous knowledge of the xy plane. Okay, so this is what we've been doing for all of high school. We've had the Cartesian plane, and we had the x-axis and the y-axis. Okay, so we're going to extend that, and we're going to extend our properties into higher dimensions. Okay, in r squared and r cubed. So r squared is 2 dimensions, right? It's like the x and the y. R cubed is the 3 dimensions, that's x, y, and z. Okay, the location of every point is unique, and therefore every vector drawn with its tail at the origin, okay, that's the standard, and its head at the point is also unique. This type of vector is called the position vector. So a position vector is when you pick up any vector in space, okay, and you position it so that its tail is at the origin. Okay, so OP, vector OP has its head at some point P, right? In two dimensions, it'd be A comma B, and its tail at the origin. Okay, and the origin is always 0, 0. That doesn't change. Okay, we know that this right here is the origin. So let's recall. The x-axis is a set of real numbers, r, which is made up of rational and irrational numbers. Okay, what that means is that the x-axis can have it's continuous and it hits every single point, every single number. Okay, so the xy plane is often referred to as r squared, which means that each of the x and y coordinates for any point on the plane is a real number. Okay, r being real number. R squared is, okay, x comma y, where, so this would be like the domain, where x and y are real numbers. Okay, it consists of every single ordered pair. Okay, now points and vectors in r squared. So vector OP can be represented in component form by the vector defined as a comma b. Okay, so this right here is called component form. In relation to vector OP, where a is called the x component and b is called the y component, right? So we're used to seeing this as an ordered pair x comma y. When we deal with vectors, we just label it a comma b. Okay, essentially the same thing. Each of the coordinates of this point is a unique real number, and because of this, the associated vector OP has a unique location in the xy plane. So, for example, if we have this Cartesian plane, okay, and this is what we've been dealing with again since the beginning of time, okay, x and y, so this is 2D. If we had some point right here, the position vector would start at the origin, and the head would be at point P. Okay, the tail would be at the origin. Now, points and vectors in r cubed. All planes in r cubed are flat surfaces that extend infinitely far in all directions and are said to be two-dimensional because each point is located using an x and a y or 2 coordinates. We can represent points and vectors in 3 dimensions as well. In r cubed, the coordinates of the point are expressed as, okay, so point vector P is going to be expressed as ABC. Okay, and its associated vector OP. Sorry, this should not be here. This is just point P would be ABC. So then if you were to take this point and you were to draw a vector from the origin, okay, now vector OP, O being origin, is going to be ABC, okay, and is a real number. The origin, again, instead of it being expressed as 0, 0, now what we're doing is we're extending it by 1 more coordinate. So instead of just x, y, we're going to do x, y, z. Okay, and again, each position vector OP is unique in r cubed, just like it was in r squared. Okay, so now we have the right-handed system of coordinates. So each pair of axes determines a plane. Okay, and each pair of planes are perpendicular. So again, a plane is almost like think of a piece of paper. And you can turn that paper any which way you want. Okay, you can turn it up, to the side, on an angle. Okay, so think of a piece of paper so paper thin that it only extends in two directions. That would be the plane. Okay. So each pair of axes determines a plane, and each pair of planes are perpendicular. Okay, we say pair of axes because there's two. So there is going to be an XZ plane, which is determined by the X and the Z axes. There's going to be a YZ plane, which is determined by the Y and the Z axes. And there's going to be an XY plane, which is determined by the X and the Y axes. Okay, planes extend infinitely far in both positive and negative directions. Okay, so this way, this way, this way, and this way. There are several ways to choose the orientation of the positive axes, but we use what is called the right-handed system. Okay, imagine yourself looking down the positive Z axis onto the XY plane. Okay, so how we actually draw this is, and I'll just do this in black so it's nice and bold. So the x-axis comes toward us, the y-axis goes to the right, and the z-axis goes up. Okay, and so these are all the positives. So positive x, positive y, positive z. And then what we do is we extend the positive x into the other direction. So we continuously go through the ZY, like the ZY plane. We continuously go through, and that dotted line depicts that they're going to be negative numbers. So this would be like the negative x-axis. Same with the y. Positive y goes now over here, which is going to be like the negative y numbers. And then positive z goes into negative z. Okay, a little bit different because if you remember, just usually an x and a y coordinate system, this is no longer x and this is no longer y. Okay, now we have y and z, and then the x is pretty much going through. Okay, so here's the right-handed system. Imagine yourself looking down the positive z-axis onto the xy plane. So the xy plane, oh, this is a good depiction of it. This is right here is the xy plane, okay? Because it goes in the x direction, which is forward and backward, and then it goes right and left, which is the y direction. So this is the xy plane. If you were to look down this way, so this is your eye, and if you were to look down onto the xy plane, so that when the positive x-axis is rotated 90 degrees counterclockwise, it becomes coincident with the positive y-axis. Okay, this is normally what is used to represent r cubed. So all this means is that this x and this y are 90 degrees from each other. So each point in ABC in r cubed has its location determined by an ordered triple. Okay, again, ordered triple, ABC. Okay, we used to say ordered pair, right? So like the XY or the AB would be ordered pair. But now we're dealing with a triple, okay? And if we wish to locate point P, ABC, we move along the x-axis to A, okay? A being that first position, okay? Whichever direction it's in, positive or negative. Then in a direction perpendicular to XY plane and parallel to the y-axis, we move to point to the point B. So you're already at point A, and you continue with that position A, and then you move to point B in the y direction. And then we continue to go. Okay, from there we move in the direction perpendicular to the xy plane and parallel to the z-axis. To the point PABC. Okay, sorry, this one was perpendicular to the XZ plane, the YZ plane. Okay, and then this point is a vertex of the right rectangular prism. Okay, I'm going to show you how to draw this. So note, if the coordinate is negative, then we proceed along the negative axis, of course. Okay, and another note, there is sometimes a confusion between whether we are dealing with a point P, ABC, or a vector, right? Vector P with that vector notation on top, ABC. We know the difference two ways. Okay, so this is how you tell the difference. Number one, note the vector symbol above the P. Okay, it's telling you it's a vector. And number two, the situation will discuss whether you're dealing with a point or a vector. Okay, so remember, a point would just kind of be three magnitudes, A, B, C, but a vector would be like magnitude and direction. So in R squared, point AB is a point that is A units from the origin along the x-axis and B units parallel to the y-axis. Okay, so in the y direction. And the position vector OP, which is AB, has its tail located at the origin and its head at the point AB. Now, in R cubed, point ABC, so these two are related, okay? So this is what we would do in 2D, in other words, R squared. Now in R cubed, if we had a point ABC, again, only extending it by that Z coordinate, okay, point P is a point that is A units from the origin along the x-axis, B units then parallel to the y-axis, and then C units parallel to the z-axis. Okay, the position vector OP has its tail located at the origin, 0, 0, 0, and its head at the point P, ABC. And then this is written as vector OP, ABC. Okay, again, the difference is this is now a vector. Okay, in this diagram, we can see that if we have point ABC, which is right here, and do this as a better color, let's go red. Okay, we moved A units along the x-axis to A, then we moved B units. It's basically along this y-axis. That's where we're going, but because we already moved to A, we just stay out here. So we draw a line parallel to this y-axis. Okay, and again, this would also be A units away. This has A units, this would be B units and B units. Now, we're located here, and we want to move C units in the Z direction, okay? The Z direction is going up and down. So if we went Z units in the Z direction, this is our endpoint. So we can clearly draw a vector from the origin to this endpoint, and that's going to be vector P. Okay, and I like to draw this complete box. I find it very, very helpful to show that we've went A units back, so these are also A units long. Okay, B across, so these ones are also B units. And then C would be up. So C would be here, 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 and here. Okay, so in R cubed, the three mutually perpendicular axes form a right-handed system. Example 1, in the diagram below, determine the coordinates of C, D, E, and F. Okay, so this is clearly 3D. We have an X, a Y, and Z. So I'm going to just set this up as C, D, E, and F, okay, with open brackets. Okay, we know that each of these is going to have 3 coordinates, and then we're going to close the bracket. Okay, and note that I did not put the vector notation over C, D, E, and F because this is just calling these coordinates. Okay, so C. So C is right here, and be reminded, so if we take a look at A goes A, 0, 0. Okay, so it's just A units away in the X direction. B goes AB, so it's B units in the Y direction. And then point P, ABC, again, C units in the Z direction. So if we're only considering C, let me clean this up. Okay, if we're only considering C, we want to go A units in the A direction. Okay, so A, and then we're just going up in the Z direction. So there's no movement in the Y direction, and then we're going C units in the Z direction. And if you notice, this right here, there's no movement in the Y direction because this is going to lie on this XZ plane. Okay, now B. So let's find the coordinate for D. So start at the origin, and we're just going up in the X direction. I don't want to put an arrow because then it looks like a vector. So we're just going up in the, or sorry, I said X, means Z direction, and there's no other movement. Okay, so this is going to be 0, 0, C. Now E. E is over here. So start at the origin. I'm going in the Y direction, so that's B. And then I'm going up, which is the Z direction, so that's C. And there's no movement in the X direction. Okay, again, the focus on the other page. If you're taking a look at this plane, there's no movement in the X direction. This doesn't come forward or backward. So E we would have 0 in that, that X slot. Okay, and now F. F is over here. Okay, starting at the origin, we just go to the right, which is in the Y direction. So the only one that we would fill in is B, 0, B, 0. So example 2, in the following diagram, the point 624 is located in R cubed. Okay, so what does this mean? R cubed, this is 3D. We see X, Y, and Z. Okay, we see 3 axes. 6 is in the X direction, 2 is in the Y direction, and 4 is in the Z direction. Okay, what are the coordinates of A, B, C, D, E, F? So this is our point, P. So we have A, B, C, D, E, and F. Okay, again, all of these are going to be coordinates. They're going to be ordered triples, okay? Not ordered pairs, ordered triples. This is in 3D. So A, going in the A direction, we only go A units away. Okay, and that's in the X direction. Since it's in the X direction, right, like there's A. Okay, I would locate, okay, so A, B, and C, we're only going in the A direction or the X direction, so it's 6. So 6, 0, 0. Now B. B is here. So we're going in the A direction and then the X direction, then the Y direction. So the X we fill in, which is 6. The Y we fill in, which is 2, but we're not going in the Z direction. Okay, for C, we go in the X direction and then the Z direction. Okay, there's no Y direction there. So the Y would be 0, and then we would sub in the 6 and the 4. Okay, for D, and remember this is from the origin. For D, we're only going in the Z direction. So we're going to have 0, 0, and then the Z value is 4. Okay, now E, we want to go in the Y direction and then the Z direction. So there's no X direction. The Y direction is 2, and the Z direction is 4. And then for F, which is here, we're only going the Y direction. So 0, 2, 0. Now B, draw the vector OP. Okay, O tells us we start at the origin, which is right here. P, we end at P, so this is tail to tip, and it looks like that. Okay, so we can label this is vector OP. Example 3. In the following diagram, the point T is located in R cubed. Okay, again, we have X, Y, Z. We have point T, which is right here. Okay, so this is now extending to the negatives. So -3 to -2. Okay, and remember, this is our X, Y, and Z. So our A, B, C. What are the coordinates of P, Q, R, M, N, S? So I'm going to put P, Q, R, M, N, S. Then we're going to draw the vector OT. Okay, so for P is going in the Y direction, right? So parallel to this Y axis. So for P, I'll draw that better. We're only going to consider this Y coordinate, which is 2. So we have 0, 2, 0. Okay, for Q, we go in the Y direction and then we go down. So we go in the Z direction. So 0 for the X, and then we have 2, -2. Okay, for R, all we're doing is going down. That's it for R. So we're just going in the Z direction. So 0, 0, -2. And you can see that this is -2 because we went down instead of up. So we are going in the negative direction. Right? M. So we're going along this x-axis for M. Okay? But we're going obviously in the negative direction. That's fine. As long as we draw it to M and we know that we are taking into account the x only, we have -3. So that -3 already takes into account that we're going in that negative direction. Okay, so -3, and then 0 in the Y direction, 0 in the Z direction. Okay, now N. So we're going in the, N is here. Okay, let's go down, which is in the Z direction. So let's draw -2, and then we're going to N, which is here. So we're going in the X direction. Okay, so -3. So that's how I saw it. But if you see it that you went here, like in the X direction, then in the up and down, which is the Z direction, you can, that's okay. I just didn't see it like that because it's way too busy in this area that I had to go down first and then up. But either way, you're going to get the same answer. Now S, we're going to go in the I see S going backwards, so that's X. So that's -3. And then to the right, which is the Y direction, which is 2. No Z direction. Okay? And if this is our point T and then this is our origin, we can draw the vector OT by putting the tail at the origin and the tip at the point T, and we can label that OT. Example 4, the point Q, 2, -3, -5 is shown in R cubed. Okay, again, 3D, X, Y, Z, and we have 2 in the X direction, which is this way, -3 in the Y direction, which is to the left, and -5 in the Z direction, which is going to be down. So this is our point Q. Okay, write an equation for the XY plane. So the XY plane is going to go in both the X and the Y directions. Okay, so in other words, it's going to be X, Y, 0. Okay, that's the general form for the XY plane. So what this means is that we're going to have a point in the X direction and the Y direction. So see this top here? This is going to be equivalent to the XY plane, except for the XY plane is going to extend in all directions forever. Okay, now, so in brackets, we can say Z equals 0. There's no Z movement. Okay, write an equation for the plane containing the points P, M, Q, and T. So PM is here, and then Q, and then T. So if we actually take a look at this, we can consider this as a plane. So we've went in the Y direction, three units. So 1, 2, yeah. So this is like -3. But this plane is in the X because it goes this way and the Z direction. So what we want to focus on here is this -3. It's located, this plane is located when Y equals -3. So the general form for the XZ plane, so let's go XZ plane, would be an X coordinate, a Z coordinate, and a 0 in the middle. But because we've moved this plane from essentially here, and we've moved it to the left, the equation for the plane that contains PM, Q, and T is now going to be X, -3, Z. Now C, write a mathematical description of the set of points in rectangle PMQT. So if we're thinking about this rectangle, okay, if we're thinking about the X coordinate has to be between 0 and 2. Okay, the Y coordinate, just like we set up here, how the Y is always going to be -3 on that plane. Okay, the Y coordinate always has to be -3. And the Z coordinate is going to be some number between 0 and -5. Oh, so I should put these backwards. -5 is less. -5 and 0. Okay, and that will take into account each point on this rectangle. Okay, and D, what is the equation of the plane parallel to the XY plane? So the XY plane goes in the direction of X, which is this way, and Y, which is this way. Nope, Y is this way. Right, so I'm just going to use this rectangular prism to show that this surface of the rectangular prism and this surface of the rectangular prism are both parallel to the XY plane, right? Because we're going in the X direction and the Y direction, okay? But it passes through the point 0, 0, -5. So we know that that -5, what's going to happen there is we're going to take this plane that, of course, extends in all directions, and we're going to move it down 5 units. So that is actually, the question is actually asking, what is the equation of this plane right here? Of course, that extends in all directions. Okay, so simply this plane, the equation is going to be z equals -5. Because every single z value is going to be -5, and you can plug anything into x and y. So essentially, every single point on this plane is going to be in the form x, comma y, comma -5. Because it's going to be, I want to kind of call it dropped, right? So like move down 5 units.